for agricultural producers. So we do industrial producers, we do agricultural producers, and then we also got involved with the Combined Heat and Power Technical Assistance Partnership. I'm the co-director of the Florida branch of the Southeast part of that Combined Heat and Power Technical Assistance Partnership in the United States. About 5 years ago, we finished a contract with the Department of Energy for the so-called Southeastern Center for Industrial Energy Intensity Reduction. And that Southeastern Center for Industrial Energy Intensity Reduction was also a DOE program, and it was very aggressive in terms of trying to reduce the industrial energy intensity in the United States by 25% in a very short period of time. That program is no longer funded, but it used to exist back between 2008 and 2013. The outline of my presentation today is one where I would first talk to you about the difference between an energy source and an energy carrier, which is sometimes confused by the bulk of the average person on the street. Then we'll give you background of the energy use in the United States in terms of how much is being consumed and what is being produced and how much the projections are for the next 10, 15, 20, 30 years. I'm going to also talk to you about the goals that are established by the Department of Energy. The Department of Energy has certain goals for by 2020 and by 2030. I'm also going to talk to you about the net zero building program. There is a status report that was published in 2014 that talks about the status of the net zero energy buildings in the United States. I'm going to briefly discuss that. I'm going to give you some examples of some net zero energy buildings in the United States. I'm going to talk to you about the house in Hawaii, Kanpuri Village. Then we'll talk to you a little bit about the so-called California experience. The so-called California experience is one in which the state of California, which has a population of about 38 million people, about slightly over 12% of the population of the United States, is moving very aggressively towards net zero energy, and I will talk to you about that. I will also talk to you about some examples of renewable energy projects that are going worldwide. I'm going to limit that to two specific topics. There are too many topics to cover, but I will limit it to only two topics. One of them is actually done in Germany, in the Fraunhofer Institute, where they are using concentrated photovoltaic thermal solar power. And then I will talk to you about some examples of projects that are funded by the Department of Energy in the area of energy efficiency in the United States. There are way too many projects going on right now, but I will select a few to talk to you about them. And then I will conclude the presentation in the end. I'm going to try to do all of that in the next 15 minutes, which is a bit ambitious, but I think it can be done. So let me see if we could do that. First of all, the topics I have selected for you for renewable energy are the hybrid CPVT solar systems, which stands for concentrated photovoltaic thermal. You all know the CPV, the concentrated photovoltaic, and you know the CSP, the so-called concentrated solar power. Now this one is a hybrid. It has CPVT, concentrated photovoltaic thermal. So it combines both the photovoltaics, the concentrated photovoltaics and the concentrated solar power in one technology. Also, we'll briefly mention the so-called solar hydrogen energy system. I'm going to tell you a little bit about that because it is relevant in this conversation a little bit. So, regarding the first slide here, in terms of what the difference is between an energy source and an energy carrier, an energy source is really a primary energy source where it is by itself capable of generating energy, or shall I say, converting energy, because energy can never be created, but it can convert energy on its own, and it exists in a form that is usable, readily available, readily usable, without having to be produced. And that is contrasted with an energy carrier, where most of the time you have to do something significant in order to be able to use an energy carrier. For example, gasoline is an energy carrier because gasoline does not exist in nature. Gasoline has to be produced from petroleum products, and therefore petroleum products are an energy source. Gasoline is an energy carrier. Another example of an energy carrier is electricity. Electricity is an energy carrier because you can't find electricity on your own. You have to actually produce electricity. You can use coal, you can use natural gas, you can use solar, you can use nuclear. All of those are primary energy sources that can be used to produce electricity. Therefore, electricity is an energy carrier as well. Also, another example of an energy carrier is hydrogen. Hydrogen is an energy carrier because hydrogen, while it's the most abundant element in the universe, it actually it is rarely found by itself in nature. There is no such thing as atomic hydrogen that you can just simply find. You can produce atomic hydrogen, but you cannot find atomic hydrogen on your own. Therefore, hydrogen is, in fact, an energy carrier as well. So that is the difference between an energy source and an energy carrier. I know that some of you know these basic things, but just in case, I wanted to make sure that we know what the rules are here. Now, let's take a look at the projected energy consumption in the United States. You can see the consumption is going up. I apologize for, okay, here you are. So I need to just show you this. This is a pretty good straight line, heading up, 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 up. You can tell that by doing that there shall come a time in the future where there's no longer the resources to actually keep going up like that. So we have to do something about that trend. That trend has to be reversed. Now you have the primary energy consumption by major source. You can see it here. And in that slide, you can actually tell that the red is the largest of all of them. The red is petroleum, 37%. Then the natural gas is 29%, nuclear electric power 9%, renewable energy only 10%. And within renewable, you've got all of those sources, all of those different technologies, geothermal and solar and wind and biomass, biofuels and wood, hydroelectric. All of those are too small. Now, this is sort of the same slide, but with showing you also the sector where it is being employed. And you can see that the petroleum is pretty much used in almost all of the four sectors. You've got the transportation sector, the industrial sector, residential and commercial sector, and the electric power sector. You can see the petroleum, the red lines are all going into all of those, and the natural gas also going into all of them. And you can see the interaction between the source and the sector in that slide. This example, this slide shows the primary energy production, not the consumption, but the production. This is where, in principle, you would want the production to match the consumption or the production to exceed the consumption. Right now, the production is about 91%. The US produces 91% of what it consumes. Now, that is actually pretty good relative to the days when I started my career. Back in the 70s and 80s, there was, the US used to import back a good amount of its energy needs. But now the US can produce, actually, quite a bit of what it needs. You can see the natural gas production, the crude oil, the coal, the nuclear, the biomass, and all of the others. This slide shows you the current and future, the current and future building consumption. In buildings, and this is where some of the people here in the room have done a good amount of the research, and of course many of you are HVAC people, and you work in air conditioning buildings. Buildings in the United States use 40% of the primary energy. That's pretty large. 70% of the electricity in the United States is also being used in buildings. Commercial buildings, the primary energy consumption grew by 70% between 1980 and 2010. The Energy Information Administration, it projects 22% growth between 2010 and 2035. That is pretty scary in some ways. Residential buildings, the homes that are built between 2000 and 2005, they used 14% less than the homes built between, or in the 1980s, and 40% less than the homes built before 1950. The areas of building energy use, as far as the commercial buildings, you can see that space heating is 45%, water heating is 18%. Then there are other smaller players. There is an asterisk on top of, you can see that asterisk. Okay, here you are. See that little asterisk? That little asterisk is an adjustment that gives you the regulated versus the unregulated. Okay, so that adjustment, this is what they call adjust to SEDs, is an Energy Information Administration adjustment to reconcile the supply side, which is the state energy data system, and the end user side. The areas of building energy use in the residential section, you can see it here, similar to the commercial. Now I'm going to shift a little bit to some of the effort. Then the International Energy Conservation Code was introduced in 1998. The latest edition, or the 6th edition, was published in 2012. And then the Energy Star program, which is a program that was designed by the Environmental Protection Agency in the United States. And the Energy Star program identifies and promotes energy efficient products in buildings in order to reduce energy consumption and reduce pollution. And then you see under the Energy Star program, there is the Leadership in Energy and Environmental Design, the so-called LEED. The LEED program, many of you are familiar with. That's a LEED certification program. It gives ratings to different buildings depending on how green they are. And then it provides technology training for high-performance buildings. Now, if you look at this slide, you will see that the reduction in energy use due to the effort by the non-governmental organizations has actually made a difference. You can see as we advance in time, you can see how much we have reduced energy, almost by 40% in 2010 relative to the baseline in 1970. Now, let us talk about the goals established by the Department of Energy. By 2025, they want the maximum energy efficiency technology to achieve the 75% energy reduction. And by 2025, they want to create the technology and knowledge base for what they call the cost-effective zero-energy commercial buildings, as ZEB or ZEBS, the zero-energy commercial buildings. That is a goal by DOE. Now, let me talk to you a little bit about the so-called Getting to Zero, the 2014 status report. This was published by the New Buildings Institute. And among the things that came in that report was a distribution of the net zero buildings that exist currently in the United States. You can see the states, and then you see the number in between in green. The number in green represents how many buildings there are that are net zero. You can see some states don't have any net zero buildings, like Montana and Idaho and Wyoming and South Dakota and North Dakota, New Mexico, Oklahoma, Arkansas, Mississippi, Louisiana, and Alabama don't have any. Then you have places like in Florida, they have 3. Texas, they don't. Texas, I don't see anything here, but Arizona has 1, Colorado has 1, and you can see Washington 2. In California, they have 10. This is, according to the Department of Energy Zero Building Database, there is 126, as of 2014, 126 buildings in the United States that have, that are classified as net zero. Now, they divided the United States into 8 climatic regions. The climatic regions that are there go from the subarctic region, which is extremely cold, the very cold, zone number 7, cold, mixed humid, zones 4A and 3A, mixed dry, hot and humid, hot dry, and marine. You can see that the distribution of depending on the climate zones, how many, the percentage of the different percentages here in terms of how much they represent. Each slice represents that percentage there. Now, these are some of the design issues that you have to account for when you're dealing with the different climatic zones. Here you have the different colors, the cold and the warm and the dry and the tropical. And then in the lower pie chart, it shows you how much the usage is for different areas like commercial, residential, and other types, and then the different classifications of versus in terms of space heating versus lighting and all of the other different uses. The 10 pioneering zero energy buildings in the United States are listed. Among them is a location in California, which is classified as zone number 3. In Vermont, zone number 6. Wisconsin, zone number 6. Ohio, zone 5. Hawaii, zone 1. Minnesota, zone 6. They cover both cold climate and warm climate. Then you've got 6 commercial buildings, 2 campus buildings, and 1 retail and 1 single family. And then the area that are covered by these 10 buildings are somewhere in the vicinity of 14,000 square foot. This is an example of the Kapuni Village, Hawaii net zero energy building. You can kind of look at what the house looks like. I'm going to get a close up in just a second. You see that in this building they have used photovoltaic panels, and they also use hot water solar panels on the roof. They also have high efficiency appliances, and they use renewable energy. And among the things that they use also is shades, what they call high-performance glazing for the shades. They use solar tube lights, and they use well-insulated walls and roofs, also light-colored so that it would reflect the sun. It does not go penetrate into the building, with a high solar reflectance. This is an example of some of the projects. They organize a solar decathlon on a yearly basis. The students actually go and build houses that are powered exclusively by the sun. And the University of Florida has participated, among many other universities, in such competitions. This is I'm going to talk to you a bit about the so-called California experience. The guy that is cutting the ribbons on his right side is Governor Jerry Brown. Governor Jerry Brown is the governor of California, is the current governor of California. He is actually a two-term governor of California. He's finishing his second term, but he was also a two-term governor of California about 20 years ago. So this is his actually fourth term as a governor. I'm not sure how they could do that, but I don't think there are any restrictions on running for governorship so long as you have to step out after two terms. But Jerry Brown is a very liberal Democrat, and he has pushed very hard to get renewable energy in California. And of course, he's pushing for zero energy as well. So their bold plan include the following. They want to, by 2020, they want to have all the new residential construction be net zero, zero net energy. So if you want to build a house in 2020 and afterward, you have to make sure that it is actually self-sufficient. For the commercial buildings, they want to achieve that goal by 2030, and by 2030, they want to make sure that all the existing commercial buildings will have been retrofitted. 50% of them would have been retrofitted to become zero net energy. Now, very briefly, because we're running out of time, renewable energy topic number one, the concentrated photovoltaic thermal. I told you about the Fraunhofer Institute, and this is a slide that I took from their website showing you how the thermal energy is harvested from the sun by itself using the traditional solar collectors, the hot water collectors. Then you have the photovoltaic is harnessing electricity from the sun. And they show you the efficiency, the conversion efficiency of the Carnot efficiency, showing you how much you lose when you do the conversion. And then they try to make a case for the concentrating photovoltaic thermal collectors, which actually do both. This is a diagram showing how they do both of them at the same time. And these are some of the installations that they have that are actually have concentrating photovoltaic cells as well as have the capability to harness the thermal side of the energy. This is a brief one slide presentation of the so-called hydrogen energy system. If you know Dr. Nejat Vezoroglu of the University of Miami Clean Energy Research Institute, you would know the history of hydrogen energy. Back in 1974, the so-called hydrogen romanticists, they gathered in Miami Beach and they fantasized about creating what they call the hydrogen economy. And in 1976, the International Journal of Hydrogen Energy published its first issue. There were 4 issues per year. They were very thin and short. And In 1989, and in 1988, the Department of Energy funded the very first renewable hydrogen program in the country. The University of Miami, which I happen to have been part of that team at the time. I worked with Dr. Veziroglu back in 1987 through 1991 on the DOE project that we got. We were 1 out of 5 institutions in the United States doing renewable hydrogen. The International Journal of Hydrogen Energy grew to 12 issues back in the 1980s, and then in the 1990s and the 2000s and above. Now the International Journal of Hydrogen Energy publishes 52 issues per year. In other words, every week there is an issue, and each issue is somewhere between 500 pages and 2,000 pages. This is not an exaggeration. I have issues that are 2,000 pages thick every week in hydrogen energy. There's a lot of people doing a lot of hydrogen energy research. So that's all I can say about that. I can tell you more about it if you're interested, but there's a whole lot more to it. Now, what is the idea? The idea is very simple. The idea is to, when you go from the primary energy source like fossil or nuclear or solar, and hopefully solar, you can produce either electricity or hydrogen, and you can transmit electricity to the end user, or you can take electricity and convert it into hydrogen and transmit hydrogen to the end user. Now, of course, renewable hydrogen, which is a program that we all would like to see, which is a solar hydrogen part of it, would be the one where you would use solar and renewable energy sources to produce hydrogen and go away from the more traditional sources. Some examples of renewable, of energy efficiency projects that are currently funded by the Department of Energy include a project on air source integrated heat pumps, cold climate heat pumps, next generation rooftop units, residential absorption heat pumps, commercial integrated heat pump with thermal storage, separate sensible and latent cooling technologies, membrane-based air conditioning systems, novel solar absorption cooling system to reduce peak loads, absorption heat pumps, water heaters. This is actually a project that we have at the University of Florida. Commercial absorption, carbon dioxide heat pump, water heater, residential absorption heat pump, water heater, combined water heater, dehumidifier, and evaporator cooler. We also have one of our faculty working on that project at the University of Florida. And many, many other projects, such as a miniaturized air-to-refrigerant heat exchanger. That's at the University of Maryland in College Park. There's a gas heat pump for building space heating. That is a company called Stone Mountain Technologies. I'll talk to you briefly about that. Highly insulating windows using smart automated shading at the Lawrence Berkeley National Lab, where they actually have shades that open and close based on the decision they make relative to where the sun is, the orientation, the temperature inside and the outside. It can actually make a smart decision for you. Dynamic windows program at the National Renewable Energy Laboratory. Dynamically responsive infrared windows coatings. That's the Pacific Northwest National Lab in Washington State. Next generation building envelope materials at Oak Ridge National Lab, and building integrated heat and moisture heat exchangers at the University of Maryland. This is, and I may have violated the very basic premise that I made at the beginning, which is to not talk too fast. So I apologize if I am talking too fast. I guess I am slowly but surely going into my comfort zone, which is to talk too fast. So my sincere apologies again. This is an example of a miniaturized air-to-refrigerant heat exchanger at the University of Maryland. And I want to talk to you about the purpose of that project. Is to develop the next generation heat exchangers for heat pumps and air conditioners. And they want to reduce the size of the heat exchanger to very small size, something you can put in your pocket, actually. And they have made some advances. This is a slide that shows you where we are and where we would like to be. If you look into the vertical axis, look at the vertical axis, you will see the compactness. What is the compactness? It's the volume divided by the area. Okay, so the smaller the volume relative to, you want to maximize the area and you want to minimize the volume. So you want to be compact. So you want to have a small heat exchanger but still has a large surface area. Now, the hydraulic diameter, which is the so-called port hydraulic diameter, is in the horizontal axis. That is a good indication of how big the heat exchanger is. You can see that there is current research in the very low hydraulic diameter, very high compactness area. This area is well investigated, which is low hydraulic diameter, low compactness. This is what current research at the University of Maryland, and this is the area where everybody has the data, like the book by Case in London, for example, on compact heat exchangers back in the 1950s. This area is well known and well documented there. And this is another slide showing the pressure drop versus the heat exchanger volume. And you can see that these are different designs for the different heat exchangers. Unfortunately, when you reduce the size of the heat exchanger, the pressure drop will go up. And heat transfer, the biggest problem you have is not just to increase heat transfer, but to increase heat transfer with minimal pressure drop. So we can talk more about that offline because we are running out of time. This is another project for the Stone Mountain Technologies, the so-called low-cost gas heat pump. I'm going to skip on that. This is the highly insulating windows with smart automated shading at the Lawrence Berkeley National Lab, where these shadings are actually smart, and they can make decisions. They have written the algorithm, and these shadings can actually open and close on their own based on many, many factors. And this is sort of how it works. This is where the algorithm is. So in conclusions, there is a lot of effort going on in finding solutions to the world energy problems. Part of the effort is directed to establishing a permanent energy system by investigating renewable energy, for example. And another effort is focused more on the energy efficiency side of things, where you are to reduce demand, not only increase supply, but reduce demand as well. The U.S. is making steady but measured progress. Under the Obama administration, there has been a lot of effort that was expended and a lot of progress that has been made. We slowed down a little bit in the past year or so, but we are hoping that we can continue pushing forward with our programs. And with this, I would like to conclude my presentation, and thank you for your attention.
Yes, thank you, Professor Sherif. We have a little time, actually, for maybe two questions, I would say. I see two hands up, so please, first question. Please use the microphone.
Good morning.
Good morning.
Dr. Sherif, as always, you did an excellent job. Thank you, and our congratulations on behalf of TTMD. I have two short questions. One is, in one of your slides, you have shown that almost all net zero buildings or nearly zero buildings are about 2 or 3 stories high.
I need you to speak up just a tad, because I'm
Sorry?
Can you speak up?
In one of your slides, you have mentioned that almost all net zero buildings are 2 to 3 stories high only. And I just wanted to confirm our own calculations that higher the building, less the chances of to become net zero. Is this a proper decision, or is it just a coincidence that all these existing buildings in the United States are low-rise buildings?
Okay, I want to make sure I understand. You're saying in most net zero energy buildings are
Yes.
1 to 2 stories high, and then
Higher the building, less the chances of becoming a net zero building.
I see. Okay. Would high-rise buildings have any chance of becoming net zero? I hope that be the case. Of course, my feeling is that we have to take baby steps. Baby steps meaning that we start with the 2 to 3-story buildings and then work our way towards the very high buildings. And I'm a believer that necessity is the mother of invention. When the push comes to shove, so to speak, we're going to have to be able to do that, or else we will have a problem. So the human ingenuity and the creativity in all of us is what is going to save us. But I think we still do not have the political decision on the part of the politicians to actually make the decision for people like us to be creative so that we can move forward. Because we have the ability to do it, but we don't have the political power, or the political will, I should say, to do it. I pray that we move into an area where net zero would be for the high buildings as well.
In SATC 74, exergy, like we are working together, we have already defined with TC 160 terminology, net zero or nearly zero exergy buildings.
Yes.
Do you see any progress on the government side in the United States about this move, or it's just no end?
I hope and pray again that exergy issues be considered in our decision making. Part of the problem we have, I'm sure that you are aware of that the political leaders, many of them do not know much about exergy and the low exergy buildings and all that. So part of what we all need to be doing is to educate, reach out to everybody and in a kind way. We have to be very kind. We cannot be arrogant. We have to be very kind, and we have to be able to communicate our ideas and convince them why this is good for all of us. So I think it behooves all of us to take that leadership position and educate in a kind way. Make sure that you come across as kind, because without that you're going to lose the message there. And besides, it's not our nature to say I am better than you because I know more than you. That's not a good idea to do that. But we have to take the responsibility of educating everybody and the average person on the street, and especially the political leaders, because they are the ones that are going to make the decision.
Thank you very much.
Okay, I saw a hand being raised from here. Oh, yeah, there you are. So the last question, very short, please, if possible.
Hi, my name is Alpay Akgüç from Turkey. You have mentioned in your presentation about zero energy buildings, their locations and their climate zones. And I wonder that what is the reason of the existence of the large amount of these buildings in especially cold and very climate zones?
Say the part of the question. What is the reason for?
The existence of large amount of these buildings in cold and very climate zones.
What is the reason for the existence of large net zero buildings in a cold climate zone?
Yes.
Okay. Well, in the case of the United States, that is actually not quite true, because the largest number of zero energy buildings is in California, which is not a cold climate zone. I think my answer is an educated guess on my part, is that this is based on the political will of the people and not necessarily based on the climate zone. It should be based on the climate zone, but what happens on the ground is that the political leaders make the decision to do it or not to do it. In the case of California, Jerry Brown and his people have decided to pursue a very aggressive net zero In other places, like in Arkansas, for example, there's none. So we have that.
And I think it is about the regulations in the states, I think.
Correct. The regulation is part of the political decision, of course.
Yeah.
Yes.
Thank
correct.
you.
Correct. Yeah.
Okay, so thank you very much, Professor Sherif.
Thank you very much.
For your Dr. Kenan Akkırman from Finnish company Halton, and he will present his work on displacement ventilation. Please.
Thank you for the organization committee and all visitors. I'm from the Finnish company Halton, and this speech will be planned by our research and development director, Dr. Kim Hekstrom, but unfortunately he had a family matters and he couldn't join this morning, and I would like to do this presentation on behalf of him. So as Halton, we are really specialized on the air distribution products in the last 50 years in Finland and all Scandinavian countries. And considering the air energy consumptions and the people spending most of the time, almost 90% of their daily life and spending in the indoor environment, and the indoor air movements are really important. And so I would like to focus on the displacement ventilation today. And before starting the overview for the displacement ventilation, I want to mention on what's the displacement ventilation, pros and cons and design methods shortly, and applications. All those research on the displacement is very important to do the thermal environment in a room with the displacement ventilation, different operation conditions. So our target is the study on the different varieties in the displacement ventilation. And then most of the experience says that and focus on the several private programs and the CFD analyze in a tool for the specific design, and shows that the increasing of the lifespan of the equipment compared to fan coils by reducing the surface temperature. And visualizing of shift zone by the CFD simulation, temperature gradients shows on the screen that now. And
Can you speak to the microphone? I think there is
Yeah.
a problem of hearing.
okay.
Thank you.
So shift zone here where air temperature increases and rapidly along the height, and the room height is so important as well. And we are spending most of the time indoor environment and high ceiling, and so the heat source and creating the heat bridge over that in the upper zone, and the thermal effects of the air direct affecting the air movement. On those research, the REHVA and our director, Kim Ekstrom, is a member of REHVA. They made their notes on the displacement ventilation all around the world, and here we want to start on our strategic design approach on the system. The room indoor and outdoor loss disturbance starting from the target of the indoor air condition and the room air condition strategy, and the air conditioning and control systems, and then back to air conditioning performance evolution. I think this is the most important part of my presentation. Here is the 4 important different way to explain the indoor climate factors and how the air movement in the indoor environment. And we can see here in the axis in the temperature, concentration, and the absolute humidity on the change on the room height. And the first one is the piston flow effect, and Second, in the important one, certification from the supply air to the exhaust air. And the third, in the zoning movement on the air. And the fourth is the mixing one. And air conditioning strategy for the mixing way, and all the heat source and the supply air comes and mixing in the indoor environment, and then creates such a comfortable and homogeneous environment. And the room air flow are controlled by the high momentum supply air flow here. And in the mixing way, in the supply air is the mix with the room air by inducing it internally in the and or externally the terminal units. And high temperature difference in the supply room air can be used in the cooling. And the mixing can be realized by the air diffuser and room air conditioning units like the ventilating cool beam, fan coils, and the induction units. And mixing supply units can be placed in ceiling, central, and perimeter of the space module. Here the wall and the face of the ceiling voids units considered to mixing effect. Residual velocity highly depend on the unit type and the placing. And air exchange efficiency here is normally between 0.3 and 0.45. Heating only possible with the right delta T and the velocity ratios. And the second strategy on the certification that we are supplying the air from the lower part of the room, and the thermal forces pushing the air to the upper zone, and so here room air flow are controlled mainly by buoyancy of the room and supply air distribution with the low momentum and low voice as well. And the displacement can be used for the stratification and the piston flow strategies, and supply air introduced into the space with the limited induction effect. Displacement can be realized by the low velocity units in the occupied zone, low velocity unit in the ceiling, and the swirl diffuser from the floor units. And displacement can be realized supporting contaminant control and or air conditioning as well. Comfort conditions in the occupied zone are affected by near zone velocities and temperature, and air exchange efficiency is normally between 0.5 and 0.8. And in this picture, the displacement ventilation air diffusion method for the certification strategy. The floor pattern in the space is controlled by the buoyance, and air is distributed gently in the occupied zone. And disturbance of the buoyance currently I avoided. This picture from France and Printemps store, and here we can see the two zones actually in the lower part, the occupied zone, and the upper part, the unoccupied zone, and we can split the zone between the red dots in the sheep zone, and the temperature gradients starting to rising up from the lower part of the room and directly to the sheep zone, and then gradually to the ceiling here. And what we are trying to mention here is that displacement ventilation in the room is directly related with the height of the above floor by its height, and heat source of the lower part of the room and the heat source in the upper part of the room, the total heat source capacities movement and changing by the heating loads. And contamination distribution quite important as well, because we are trying to create some comfortable environment, and then all we want to be in living in the healthy and well-being environment for our lives. And here that I want to mention that contamination rates is increasing by the air movements in the indoor environment as well, from lower part and going to all occupied equipments that we focus on the computers or our business through the sitting level. And of course, in the different mechanical settings in the air distribution and the conditioning systems, that cooled ceiling panels combined with the displacement ventilations as well. And here is that one lower level cooling supply areas comes from the lower part of the room, and of course some other extra cooling ceiling panels gives the effect, and more cooling energy is taken from the ceiling by the passive beam system, and smaller temperature and gradients in the room space. And here's the in the graphic, in above the flow level, by time and by height and the change of the ratio, the cooling ceiling output to the total cooling output ratio. And the design methods of the indoor environment in the temperature-based design for the thermal comfort that we are used when the heat and considered to be the main source of the contaminants. And here's the information about heat source of the limited units, and this we are focused on the, of course, energy efficiency here. And shift zone base for the air quality used when the shift zone has been above human breathing level. Detailed information about the heat source is needed. So I will show some more pictures about some applications. Design of the energy efficiency and the temperature-based method, and is shown in the picture in the occupied zone in the low level and the unoccupied zone in the above level, and the movement of the heat loads and the mass of the air is given in a balance for the room energy protection. And the design for indoor air quality shift zone method, everything's from the temperature-based design here. And the shift zone design is directly related with the heat loads in the indoor environment. And the shift zone method here, of course, the thermal effects considering here, and conventional flow at the vertical face from the wall side and the hot wall side or the cold wall side. And those effects are coming from down to upper part and upper to down part. And temperature and the humidity gradient in the hot and humid climate is given in several graphics. And the pros is the displacement ventilation is the less cooling energy is needed, is about 10 to 30%. And the longer free cooling period and better air quality and thus better productivity for the workers. Beside the pros of the cons, there's no advantage if the ceiling height is less than 2.5 meter. And near unit draft risk and velocity should avoid the analysis, and enough space for the unit should be available. And displacement ventilation actually, as we think on that perfectly for the VAV applications, because it's quite well adapted to variable air volume systems, and the supply air pattern in the well managed within the wide airflow range. For example, the airports and the big shopping malls as well. And alternative control concepts, temperature control principles, and air quality control principles. And shortly, I'm ending my speech with the, some application pictures in the smoking lounge, kitchen, restaurant, auditorium, atrium, gyms, and more. And here is the one example. It's the atria and the other high ceiling space. And lobby areas, as you can see the installed units from the down level on the France and the public areas, public spaces, airports, because unoccupied zone is quite important in the above level, and architects designing quite high ceiling. And actually it's very important for the theaters and auditorium considering the noise criteria and the thermal comfort effects, including the ballrooms like we are in at the moment, and the different working environments like for spaces where there's a high heat loads together with the big import sources around and factories as well. And the smoking areas similar, like because of the supply air location is important of the not to take the air over the room. And for, of course, this is very important for the children and for future generation in the classroom and the schools. And just a few more picture about supply air contained between the rows. Supply air is floating down from the stairways here. And low velocity units, a shape for the everyday application, as can seen in the pictures, in the quite low sound levels and easy and fast install, heavy duty and metallic construction. And we want to focus that and finalizing my words about it, and the energy efficiency and how any single electricity bills comes from the fan coils or the other VRF, other cooling environmental equipments are going to wasting the money in somehow. And the ducting through floors, and here I want to show one example here. You can protect your environment and energy consumptions. And here's one more from the ducting through, but hidden one. And the flow pattern of some units, height of the units, and supply temperature influence of the flow patterns. And this is the same like as I mentioned before. And heating design is the last, when heating is needed, duration in time versus cooling, and continuous or temporary is important, and during the occupation and standby only. And specific requirement for the heating mode, can sound level, indoor climate requirements to be released for heating period, mode shift in the terminal manual and or automatic, and integrated or disintegrated heating function, avoiding downturn from the glazed facade by the constructional solutions.
Okay, so thank you for your presentation. We're kind of running out of time, or we ran out of time actually, so I will leave the questions.
European 2020 strategy, there is about the energy. Three objectives is reducing greenhouse gas emission 20%, also increasing the share of renewable energy in the final energy consumption, also 20%, and moving towards 20% increase the energy efficiency. In 2015, European greenhouse gas emissions, is including international aviation, indirect carbon dioxide were down by 22% compared with 1990 year of the 1990 levels. Also, in 2020, EU expected exceed in its 2020 targets of reducing greenhouse gas emission by 20%. All sectors except fuel combustion in transport and international aviation contribute to reduce reductions between 1990 and 2015. Renewable energy in Europe. Renewable energy is also rise in European countries. Gross final energy consumption from 8.5% in 2004 and nearly 17% in 2015 years. Renewable energy share range from nearly 15% in Sweden, also it's only 5% in Luxembourg and Malta. This is also small countries, is Luxembourg and Malta. Electricity from solar and the wind project increasingly compared with fossil fuel-based power generation. European countries' houses heating and cooling. Heating and cooling concept in residential and industry. In European countries, the total demand for heating and cooling houses in 2012 amount in 546 MTOA, representative half of the total final energy consumption in European countries is also 1,100 MTOA, residential mainly household buildings, presenting highest share in the cooling heating. Final houses, final energy heating and cooling consumption in 2012 in residential sector is nearly half. Industrial share is 37%. Service also 18%. In agriculture sector is not included in service sector. The share of industrial is total heat consumption about nearly half in Spain, Finland, Portugal, Slovakia, Austria, and Sweden. There is not regular, is some countries, is the Mediterranean countries, is Spain, Portugal, other countries is also cold. Finland, Sweden, Austria, I don't know what is. This, especially, space heating is nearly half, and heating and cooling end use. Process heating also 1/3 is heating and cooling end uses. Hot water is nearly 9%, sorry. European houses, European community houses, heating and cooling, comparison of final energy demand for heating and cooling end use reveals substantially different across the countries. The share of process heating variety from 15% Estonia and 56% in Portugal. It's not logic, I think. The Estonia is the cold country, so the Portugal also is the Mediterranean hot climate countries. Space cooling shows clearly peak in Mediterranean countries, maximum in Greece, Malta, Cyprus is southeast countries of Europe is nearly 9-10%, but the Malta and the Cyprus more than 10% is 19, also 33% is the tourism is important in, I think, these countries is the Cyprus and Malta, also Greece maybe. 15, the total energy consumed our houses is used for non-heating and cooling uses. Heat is used houses to provide warm and hot water and cook in the food. Satisfied space heating and hot water recommends supply temperatures below 100 centigrades. Sufficiency. This is the area of the residential service sector and the industrial in the European countries, but it is not. It is also certainly a little bit different. The service sector is 2% is different. Residential percent is also. But nearly is equal. There is no special areas. Is certain areas in European countries, residential service sector and the industrial sectors area. Space heating in the residential sector. Space heating in the residential sector is biggest share, 79% of total use, final energy use. Very big energy use is the space heating is 79%. Cooling is very little. Cooking and the hot water is also the second big percent. Since 20, energy consumption for space heating declined by 12%. Is efficiency of household space heating and measured in kilowatt hour or gigajoule per meter square improves steadily around 2.3% per year in European countries level. 2. Focus on spatial solution for heating and cooling. In European is the linking building and industry to use waste heat. The total waste heat. The second use the waste heat in primarily is food supply and refineries, industrial facilities, chemical and petrochemical, iron and steel, non-ferro metals, non-metallic minerals, papers, printing, and the food and beverage sector. This is the second is the district heating. Today nearly 70 million European citizens are served district heating systems. 9% heating residential sector, 10% service sector, and also 8% in eastern industry. The third is linking heating and cooling electricity systems. The four high efficiency cogeneration systems. The efficiency of cogeneration systems can reach 9% or above. And finally, is the passive and active technologies integrated and to control heat and control supply in buildings and industry. Conclusion is the European countries is home is largest energy importance in the world, and former Eastern Bloc countries as member of in 24 and 27, and sheltered in the program in 27 to solve their problems before the bad energy performance and depends on important energy. The program aims ensure to countries save energy nearly 15% in 2020. This also large targets increase their renewable energy rates 8% in 2020 to 20% in 2020. Also, especially carbon dioxide, especially carbon dioxide reduced in these countries is improve their healthcare systems. And Turkey will maintain its also relation with the UAE like Britain and Switzerland, and there is as the act parallel with the energy policies of the European countries. It's obliges the largest saving capacities in that buildings. The use of the new technologies and the insulation applications, especially architecture, looks promising in the terms of potential. Thank you.
Yes, thank you very much, Professor Batur. We have maybe a question for one question, if there is any from the audience. If not the case, we thank you, Dr. Batur.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen. First of all, I would like to thank TTMD for having invited me and for giving me the opportunity to do this presentation. It's an honor and a pleasure to be here. Thank you very much. I will talk about building envelope, a future beyond the concept of thermal insulation. And okay, let's go through some points why it is important to talk about building envelope, how building envelope and energy efficiency was tackled in the past and is partly tackled today, and how it should be, at least how our research group think it should be done in the future. Why is important? Because, as you may know, in many countries, the energy consumption related to the building is the big quota of the overall budget, and it represents more or less 40% of the end use of energy. And if we look in more detail at the building envelope, we see that for residential building, we have the possibility of achieving about 50% of energy saving in the residential sector, but because it accounts for 50% of the overall energy demand, mostly for heating. While in commercial building, this quota is about 30% of the overall energy demand. That means heating, cooling, appliances, and it's also very important in commercial building as far as natural and artificial lighting is concerned. And if we look at buildings, especially I have the figures for Italy, that have been built before the energy conservation law, that is before the 80s, the possibility of improving the energy efficiency of a factor of 50 to 60% is very high, and the payback period is very low. So it's convenient not only from the point of view of energy efficiency, but also from the point of view of economy. And where the biggest potential lies, again, if we look at the figures, we saw that in Europe, the construction rate of new building is around 1%, and this figure is even much lower in Italy, is around 0.5% as a magnitude. And the buildings that are built in this field are very energy efficient, are between 30 to 50 kilowatt hour square meter per year. But the existing buildings are really poorly performing. So retrofit, at least in Italy and in Europe, is a very key factor for achieving energy efficiency, more than new buildings. What are the challenges to implement the energy conservation policy as far as the building envelope is concerned? They are the typical one, so technological challenges, lack of understanding and knowledge, design tools and method. We saw yesterday very interesting presentation about the needs, the requirement of new software tools or new specification. Absence of requisite skills, both in terms of design procedure for new component and construction skills. And finally, cost. I put cost as the last one because frequently cost is claimed to be the driving factor that prevents new technology to be installed. Actually, sometimes costs derive from the absence of skills. So if skills are there, cost goes down. If the volume of new technology installed increases, cost goes down. So in my opinion, cost is just a problem now, but it's not a real barrier. Nevertheless, innovative concepts are needed to implement low carbon technology. But not only to save energy, they are also needed to improve the indoor environmental quality and to achieve healthy and comfortable living spaces. Sometimes we are so focused on the energy saving issues that has been strongly implemented by the EBPD, for example, in Europe, that we are forgetting that buildings are built for people, not for saving energy. So first of all, our task is not saving energy, but it's provide comfortably healthy buildings, and then doing this with the less use of energy possible. How it was? If we look at the definition that you can Google on internet about the building envelope, you see some of these sentences. The building envelope was meant to provide thermal shell to protect, to separate the indoor environment from the outdoor. It's a shelter. It's something used to fight against an hostile outdoor climate. And we have not to forget that when we are talking about building envelope, we are talking not only about facades, but also of foundation, piles, structures, and so on. And all these elements as I will show you, can give us opportunities for finding new technologies that are better in terms of indoor environmental quality and energy efficiency. So if we look at the main function that was so far given to the building envelope was that of separating. It was a physical protection, so that meant that the best possible design of a building envelope was the one who provided the highest disconnection between indoor and outdoor. So the envelope was a concern, was something to fight against. And all these ideas led to the same philosophy that was, let's solve the problem, increasing the thermal insulation of the walls. If we look at the history, we also find an interesting point. If we look at the past, the traditional architecture, you can see here, this is a typical rural architecture of north of Italy. It's near where I live. At the time, shortage of cheap and easy to reach energy vectors, low efficiency of energy converters, and low expectation of people. That meant just wanting to have some heating during winter, led to design the building in order to exploit as much as possible the local climate context. So for example, here you can see the south-facing facade was drilled with glass to improve the free gains. The north side was all opaque walls to isolate as much as possible the worst side of the building, and this is reflecting, as you can see, the heating degree day, the local climate context. So in the past, heavy non-insulated masonry walls were able to provide the basic thermal insulation, and fenestration were less advanced, and so they were poorly performing and less used. So here you can see what the architecture resulted in. Very massive wall, massive building, large opaque surfaces, small window. But with the evolution of technology and the trend of modernism, new materials, new technological construction were available for designer, and that meant that solid walls started to be drilled more and more by holes that were occupied by glazing. So dark, heavy, old-looking, opaque walls were turned into light, modern, transparent fenestration or glass walls. This is the, let's say, era of the enthusiasm about the technology. The idea was, who cares about the building envelope, because then there is a mechanical engineer who will take care of the indoor air conditioning with very efficient, big, huge HVAC system. But this is not the solution. This is not the best solution at all. This innovation, still the one of glazing, and the innovation in the 70s and the 80s, still abide by the concept of thermal protection of barrier. And the availability of easy to install and quite efficient HVAC system forced to design the building envelope with the principle of one size fits all. Who care about the climate? Who care about the exposition? I build the building and then I will install the mechanical system. So it's the flourishing of very high glazed building we can see all around. And this is also due to the fact that architects started to copycat the ideas of very VIP famous architects who wanted to have this very iconic glazed building. But this resulted in beautiful building, but frequently poorly performing in terms of comfort of people and energy efficiency. I propose you a puzzle game. Let's suppose there's someone cuff your head and carry in a place in the world and then uncuff you and let you looking at the building. Can you guess where are you if you are looking at this building? First one? This one?
Nordic countries.
Oh, Denmark. Yes, close. This one? Greece, okay. This one? Norway. And this one, Turin. You did a good job. This is Belgium. This is Greek island. This is Norway, Trondheim, and this is north of Italy. Now, let's repeat the gain. And as you can see here, they reflect the climate condition. Heating degree day and cooling degree day are coherent with the building envelope. Let's do the same. Where are you if you are looking at this building? Can you guess? Maybe you can guess because some of these buildings are very famous because have been designed by very famous architects. But surely you can't guess by looking at the envelope technology. And actually, one is Brisbane, Hong Kong, Seoul, Toronto, Tokyo, Helsinki, New York. They look all the same. They are the same. But the climate conditions are far different. This is a problem. I mean, for sure, all of you can design a good HVAC system that can take care of this climate condition, but for sure, the HVAC system and the building envelope are not in tune. I mean, it's a forced marriage. And problem arises, because if you have a glazed facade like this one, in a very hot environment, you need a huge HVAC system. Huge HVAC system means a lot of airflow rate. A lot of airflow rate means a lot of problems about draft, concerns of people, radiant temperature, because you can provide correct indoor temperature, but radiant temperature is not correct. So it's a problem. That means that the energy conservation approach that have been used and the forgetting of the local climate is a problem. And the limitation of this, of all these ideas are coming now in front of us. First of all, if you look at the building, new building, especially high-rise building, severe problem of overheating occurs even in cold climate. Even in Stockholm or Oslo, such kind of building needs to be cooled during the winter time. A significant increase of the cooling loads is observed, and transmission losses are becoming lower and lower compared to ventilation losses. If you plot for Italy, the trend of the transmission coefficient and the ventilation coefficient losses versus time, you see we are more or less here. So today, transmission losses are more or less at the same size of ventilation losses. So thermal insulation is becoming less important. And beside this, it's not only a question of tackling the heating demand, it's a question also of taking space cooling, lighting, and plug loss. So today, a total energy approach is needed. Because if you optimize heating, you're going to unoptimize cooling and vice versa and lighting. So we need to take into consideration all the voices of the energy demand altogether and do a total energy optimization. Moreover, what happened during the year? Since we pushed over and over this thermal insulation increase, we are now facing the consequences of the so-called law of diminishing returns. This law comes from the economics and says that if you are continuing optimizing a process, you reach a level at which further benefits are achieved only at the expense of huge investment. So if we look at the trend of the cost of insulation mandatory by law in Italy, this is the trend during the year. That means that if in the 70s you had some money in your pocket, this money here, and you decided to invest in a better insulation of the building envelope, you could get this improvement because you were moving in this area. But if today you have the same value for money in your pocket and you invest into the insulation, you are moving in this area, and what you can get is very, very small improvement. So the idea of increasing the thickness of insulation on and on and on is not anymore a good idea, is not anymore an efficient way. We need to revolutionize the concept. We have to go beyond the one-size-fits-all approach, and we have to think starting that we have to work with the climate, not against it. A paradigm shift is needed. We have to move from a passive, totally passive approach to active approach in which the building envelope is not anymore a consumer of energy, but is also a producer of energy or an energy storage. So we have to switch from the insulation concept to that of integration and multi-functionality. So let's come to the how should be, at least in our ideas, then maybe someone is not agreeing with us. First of all, so far the building envelope has been seen as a problem. This is wrong. It's an opportunity. I heard a very interesting point on this from Professor Ray Cole from Canada. He said, if Martin Luther King would have said, I have a nightmare, his result would have been far lower instead of his fantastic speech when he said, I have a dream. That's the problem. We have to turn this concept. The building envelope is not anymore a problem, it's not a nightmare, it's a dream. I have a huge area that I can exploit to install new technologies, to install renewable energy sources technology to exploit, and is the huge interface between the indoor and the outdoor environment. So it's a huge opportunity. We, however, have to start thinking at it in a different way. Technologies are there. Nothing is completely new. You can see here some examples, just some. Solar space, smart glazing, electrochromic, thermochromic, thermotropic, embedded duct, earth coupling, thermal mass activation, PCMs, active roof, active walls, dynamic walls, dynamic insulation, trombe walls. So there's a lot of opportunities to be exploited. The question is, we have to take all these pieces together that now are frequently look separately and to put into a coherent integrated design. This can be done at different level. The first one is concept level, the second one is a system level, and the third one is at material level. The time is short, so I will just give you some flavor of what can be done, looking at some example at system level or at material level. Here, for example, is a multifunctional facade module. It's called Actress. This is clearly an architect's idea because it's actress, like an actress, she can play different roles. Architects are very creative in this. He's a colleague of mine we work with, and we developed this facade. By the way, it was a joint project also with Livio Mazzarella. It was financed by the ministry in Italy, and it's a prefabricated facade module, 50% opaque, 50% transparent, and it included a number of technology. The opaque part, as you can see here, is a ventilated facade that includes amorphous PV cells, very efficient insulation with a small thickness using VIP, vacuum insulation panel, and two different kind of PCM to store energy. The transparent part, this one, it's a triple glazing with aerogels to have diffuse lighting in the upper part and low E coating with a Venetian blind in this one. I can't go through the details, but just to give you an idea, this can be used in a flexible way, so when you need to have very high thermal insulation, it may happen during low solar radiation day, winter day, you can close the ventilation, or you can use the facade as a solar air collector to preheat the ventilation air by natural ventilation, or when the solar radiation is very high, by mechanical ventilation, activating the fans through the PV. And during summertime, when you need to reject solar load, you can use the so-called outdoor air curtain by mechanical ventilation when the conditions are very tough, or natural ventilation where the conditions are milder. And here are some figures simulated. This module allows to have an electrical energy reduction of about 52%. It allows to have significant reduction in heating loads, and by using the PV coupled to the PCM to store energy and exploiting the ventilation air, you may save an extra 8% of energy for heating. Here are some measured data of energy crossing the facade. As you can see, during winter it works very, very well. Most of the time you have gains instead of having losses. It's a little bit still to be optimized during the summertime, since the entering loads are not very high, but still are higher than we would like to be. There are different examples. Here is that one was a prototype. This one is a real facade. It's a two-story facade installed in an office building in the northeast of Italy. It's strongly integrated with the HVAC system, so you can see here different strategies to use the facade either as a solar collector to preheat the ventilation here, or you can use it as an exhaust duct for the air handling unit in order to have dynamic insulation of the facade during summertime, so you can save energy, and at the same time you decrease the radiant temperature both in negative and positive side during winter and summertime. And we did a 2 year of measurement, also having interview with occupants, and it performed very well, both in terms of energy saving and comfort. Here is a blow-up of the scheme. But there are examples also, again, prototype of using water. For example, this is a water window that has been proposed by Cho, a colleague from Hong Kong University, that used glass facades of some high-rise building with the idea of preheating water for domestic hot water production, for example, and to cool the facade. Clearly, not easy to tackle the technological issues related to the real application, but still there are examples. Maybe Manuel knows this one. Is in Lisbon. It's near the railroad designed by Calatrava. It's a huge shopping mall. It's a courtyard that has been covered with a transparent roof, and this roof is cooled by water. As you can see here, water is flowing all over the roof, and it works very well. I've been there 2 or 3 times. I took this picture in July with a lot of solar radiation, and the just sheet of water acts on one side as a solar collector, and on the other side cools the facade. Clearly there are some problems. For example, seagull resting there, that needs then maintenance of the system. And then you may also work at material level. Here is a prototype of glazing including PCM that may collect solar energy. You can see the PCM melts during the day, and then it freezes during the night, so it avoids solar load entering during the day, but allows daylighting to be achieved in a diffuse way that is good for the quality of light. Here you can see the performance. The blue one is a normal clear glazing, the red one is the PCM glass, so you can reduce the peak load during the summertime by large extent with this technology. There are even other sophisticated technology like thermoelectric system coupled to PV and so on. I will just skip this. Coming to the end, what we have done so far, we can be resumed in this picture. So we pushed a lot, increasing thermal insulation. We did very well. We achieved very high-tech solution. And today, you can go to the Everest or you can go tourism in the Antarctic feeling warm. So I said, okay, it's fine. But would you like to be here, dressing this clothes? I don't think so. Usually what we do is this. During winter, in the Antarctic, I increase the thermal insulation, but then I adapt. But why, if you are doing this to yourself, why we are not doing this for our building? Today, our building behave like this one. And when they are at the seaside, they are not performing very well. So adaptive, integrated, dynamic building components are required in our opinion. There are clearly problems of indicators. I skipped this one. U value is no more feasible, so we need new way of assessing the performance. We heard yesterday very well, and I completely agree. And coming to the conclusion, it's mandatory to overcome the paradigm of the energy conservation approach that leads just to increase the thermal insulation. We have to see the envelope as an opportunity, and it has to be adaptable, multifunctional, integrated with the HVAC. And this asks for changing the mind, and we need to translate ideas and prototype into facts. Is it a visionary utopia or the real future of the building envelope? There are indeed a lot of difficulties. Lack of tools, absence of standards. We heard very well yesterday, and it's really true in this sector. Lack of skills, lack of synthetic indicators to score the performance of the component, poor knowledge, and so on. Cost, even if we discussed before, it's not always a problem, but isn't this the usual situation when we are looking at the really step forward in the technology? Maybe. I like this sentence by Henry Ford, who at the beginning of the car era, he said, if I would have asked my customer what they wanted, they would have told me faster horses. But the solution wasn't breeding faster horses. The solution was completely changing the idea. And is what happening today. Even as economic model, I told you about cost. Cost cannot be a problem. I know that in the Netherlands, for example, recently, companies are starting to introduce a new market idea in which the facade is not bought by the owner of the building, but is rented, like cars. If you go to buy cars today, at least in Italy or in Europe, most frequently the car dealer is not selling you the car, he's selling you the service. You get back your car to the customer, you take a new car with couple of thousand euros, and then you pay a fee for 3 years, and after 3 years you gave back the car. Why? Because cars are evolving very rapidly. For example, diesel engine maybe in 5 years will be banned or restricted in Europe. So who is going to buy a car that in a few years becomes old? And the same is happening in the facade. Facades are evolving very rapidly. There are companies who are renting the facade for a period, and they are gaining in the energy saving of the building. Thank you so much for your kind attention. Oh, sorry, I was going to forget one thing. There is a project running in Europe, is a cost action about adaptive facade, and it gathers 26 countries in Europe and everywhere. If you want to have a look at this idea that we are developing in this group, you can refer to this website. Sorry. Thank you so much.
Thank you very much, Professor Marco Perino, for this very valuable presentation, especially stressing the importance of architecture. Actually, that is the most important and the crucial point and step of the energy efficient design. So architects are boss, I have to say. Kemal left the room. I hope he has heard. No, he is here, already here. He has heard. He is still talking to next to him about insulation. You are agreeing with me, especially for the cooling loads. Insulation is not a good solution. So we can get a few questions, and in the meantime, unfortunately, I forgot, I have to remind, you have to fill out the questionnaire, which has been sent to the mobile about your opinion for this session. So please don't forget to fill out the questionnaire through the link which has been sent to your mobile. So we can take some questions maybe, so we don't have that much time until lunch. Questions from the audience?
Just a question about your actress facade. So, for instance, if we were using it in a retrofitting process, do you have an estimation of the payback time, or should we rent it?
This is a good question. Difficult to say. This project was done together with the manufacturer of technological facade module, and one input they gave us, for example, they told us that the construction is a key issue for the timing. So, for example, the module was self-contained. So it was just a question of arriving and hanging the module on the building. So if you are going to retrofit an existing building, tendentially a high-rise building in which an already installed technical facade is there, it's easy to install. The cost, difficult to say, because this one has been built as a prototype, so buying one pieces by one pieces. And the economy of scale is very important. I mean, if you are going to buy a GPS, for example, you are going to pay at least €100. But if you buy 100,000 GPS sensor to be installed in a mobile phone, they cost less than €1. So this facade, if I'm not wrong, costed around €10,000 to be built, but built pieces by pieces, asking specialists. We had an estimate that it was a little bit less expensive than normal ventilated facade, but still feasible at this time. But I don't have the specific figure.
Okay, thank you. Any other question? That means we have to conclude, okay.